Well, hello and welcome back for the next short lecture on fracture and fatigue. Today we'll be taking a look at fatigue behavior. Fatigue is essentially the fracture of a material under dynamic stresses, so as opposed to static stresses. So in dynamic situations, you have a stress that's on the material and then we take the stress off the material. We put it back on the material and we take it back off the material. And by doing this, what we do is we actually create damage at the tip of a crack, and that crack has the ability to grow under the fatigue conditions. So fatigue is the failure of a component by the growth of a crack within a material under dynamic fluctuating stresses. Now think back to the previous topic where we discussed fracture mechanics, and we said that the stress intensity of a crack is dependent on the size of the crack, at least partly. If a crack can grow, that means the stress intensity can also grow. So failure occurs when the stress intensity grows a high enough value that it reaches the fracture toughness of the material and fracture ensues. Generally though, fatigue crack growth occurs at stresses well below the ultimate tensile strength, the yield strength, and even the critical stress for the original crack. So in other words, the stress can be designed to be very, very low from normal static testing considerations. But the truth of the matter is that if the fatigue is present, if there are dynamic stresses, then fracture can still occur unexpectedly. The number of stress fluctuations, or what we call cycles, that a part can survive before fracture can range from a few hundred to billions. Think of, for example, a paperclip. If you take a paperclip and bend it back and forth, eventually you'll snap it in half. It doesn't take very many cycles for this to happen. This is called low cycle fatigue. But an engine block can take billions of cycles before it develops a crack and eventually fails in fatigue. But each of those cycles is caused by the vibration of the engine, so those cycles are put on very quickly. This is a situation called high cycle fatigue. It turns out that 90% of failures in metallic components and many in plastics occur by fatigue, accounting for billions of dollars in losses in industry. So let's take a look at how we actually predict fatigue behavior. Generally, we produce a plot called an SN curve. An SN curve has the number of cycles to failure down here on the x-axis, always on a logarithmic scale, and the stress amplitude, or how much stress is applied cyclically to the material, on the y-axis. It turns out that all materials start out with a high stress amplitude at low cycles to failure, and that as the number of cycles of failure increases, we have to reduce the stress or the material will fail. In other words, if I'm on this side of the line over here, I'll have failure. Let's write that in. I gotta get better at writing with this thing. So anywhere above this line, we have failure. So for example, if I had a material that I wanted to survive to 10 to the 6 cycles, I draw a line straight up from that point, I would have to design it to be below that stress level. Otherwise, I risk the possibility of a failure. Now, ferrous metals like steel have a special property called the endurance limit. The endurance limit is the stress at which, as long as I'm below that stress, I have infinite life. So down here, we are in an infinite life regime. No matter how many cycles I put on the material, as long as I stay below that stress, I won't fail. And the reason for that is that below that stress, cracks are unable to grow. Non-ferrous alloys like aluminum and titanium, however, do not exhibit a fatigue limit or endurance limit. Instead, they have a continuously decreasing curve, so that no matter how much I lower the stress, eventually I'm going to fail in fatigue if fatigue dynamic stresses are present. So there are two properties we could measure from this graph. We could look at the fatigue life, which is the number of cycles to failure at a specified stress, So for example, if I said stress is S1, the fatigue life would be measured by coming down here. Or if I have fatigue strength, I go to a certain specified life N1, go up to the curve and over, and that's our fatigue strength at N1 cycles. It's the maximum survivable stress at a specified number of cycles. So once again, the important thing here though is that in non-ferrous metals like aluminum and titanium, there is no endurance limit. The possibility of infinite life does not exist. We also have to be really careful when we use SN curves like this. It turns out that fatigue is very, very difficult to predict. There's a huge amount of scatter in the data. If you've ever done fatigue testing, you can be assured that you know this fact. So when we plot SN curves, it's often a good idea to plot what are called probability SN curves, or multiple lines which represent the probability that a part will fail. The lowest SN curve on this plot, shown right here, has a probability of 0.01. That means that 1% of the samples will fail when they reach that curve. Compare that to this top curve, which has a probability of failure of 0.99. And that means 99% of the samples will have failed when they reach that curve. In between is a whole range of probabilities. You can see that the probability span is rather short. In fact, at high stresses of say 400 megapascals, there's a very narrow range. If I can draw this line down, a very narrow range over which our samples will fail in terms of the number of cycles to failure. On the other hand, if I'm at a lower stress, let's say 200 megapascals, there's a huge range of failures. Everything from just short of 10 to the 7th cycles to more than 10 to the 8th cycles. That's a massive range of number of cycles to failure. And of course, when we design products, we normally design them to be at lower stresses where they're less likely to fail in fatigue. So here we are designing a product at a stress of 200 megapascals, and we can't predict how close it is to failure within a lifespan of 2 orders of magnitude. That's a big problem, and it's why we spend a lot of money trying to understand fatigue behavior. Next time we'll look